Okay, so today we're going to move further out from the sun. We've talked about the terrestrial planets, and now we're going to start talking about the gas giants. So these are the Jovian planets, and today we'll start with Saturn and Jupiter. So here's kind of a family portrait of the four gas planets. So Jupiter, Saturn, Uranus, and Neptune. So today we're going to talk about what the gas planets are made out of and talk about the weather that we see in their atmospheres. So the Jovian planets are mostly made out of hydrogen and helium. And in Uranus and Neptune, that hydrogen is in the form of compounds with other chemicals like oxygen to make water, carbon to make methane, and nitrogen to make ammonia. And then there are some metals and rocks in the gas planets as well. When we talked about the nebular theory for how the solar system formed, we said the rocky planets formed closer to the sun because they're within the frost line. And basically anything that's too close to the sun, if it's not made out of a material like rock that has a high melting point and boiling point, then it will basically all evaporate and you won't be able to form a planet out of it. But farther away from the sun, the temperature cools down, and now you can get things like ices forming, and there will be a lot of free gas farther away from the sun. The sun is gobbling up a lot of the gas in the inner solar system, but there will be lots of excess gas out further away that you can make gas planets out of. So the cores of all of the gas planets are very similar. They're all about 10 times the mass of the Earth. The core is kind of what you start making your planet out of, but then the gas that's around that core is different between the different planets. So we need to explain why, for example, Jupiter and Saturn are more kind of a brown gold color, and then Neptune and Uranus we see more of a blue color. And that's indicative of what gases those planets are made out of. So the big differences are timing and location for planet formation. So timing, whichever planet starts forming first or gets biggest first is going to capture the most gas that's available. And remember, it's kind of a race against the clock because the center of your nebula is collecting gas, and eventually it's going to turn into a star, and once the star turns on, meaning starts doing nuclear reactions, it's going to blow any leftover material out of the system. So you're in a race to capture as much hydrogen and helium as you can before the sun turns on. And then where planets form will be pockets of density in your nebular cloud, and the denser regions will start to collect more material first and lead to bigger planets. So Jupiter is the first gas planet out from the sun, and it's also the biggest. So it was in probably one of the denser regions of the nebula, besides the center where the sun formed. So it was able to collect a bunch of the gas around it and become very large. So this is what it looks like in infrared, visible, and ultraviolet wavelengths. We can really only see the atmosphere of Jupiter, so we can see the cloud tops but there's a lot going on inside of the planet. So as you go deeper into a planet, your density is going to increase, and your pressure is going to increase. So at the top layer of Jupiter, your hydrogen is just in a gas form, like you would have gas in our atmosphere on Earth. As you go deeper, the pressure increases. If you increase the pressure on a gas, you can change its form from a gas to a liquid. So then you have a layer of liquid hydrogen. If you keep increasing the pressure on the hydrogen, you can have another phase transition where now the hydrogen starts to act like a metal. So hydrogen we don't usually think of hydrogen as a metal. It's got one electron and one proton, but if you increase the pressure enough, you can kind of free that electron, and now you've got basically a sea of electrons that are free to move around. And when we talk about metals are materials where the electrons are free to move around. So that's how like electrical wires work, is you have a lot of electrons that are free to move around, and when you put a current through it, those electrons can move. So we have in Jupiter and the other gas planets, we have a layer of metallic hydrogen, and then further down from that, you have a core that might have some denser materials, like a little bit of rock and metals, but for the most part, it's all hydrogen. And to give you a sense of scale, if you were to put the entirety of the Earth next to this cross-section of Jupiter, the core of Jupiter is bigger than all of the Earth and its atmosphere and everything like that. Jupiter has, besides the sun, Jupiter has the strongest magnetic field in the solar system, extending way beyond the planet itself. And so we can see, just like we have auroras on Earth, there's auroras at the poles for Jupiter. And again, we get those auroras by charged particles coming from the sun. They get trapped along these magnetic field lines, and those field lines terminate on the poles of the planet. There's also material from some of the moons that are orbiting Jupiter that can feed material along the magnetic field lines to create auroras as well. And so to give you a sense of the scale for how big Jupiter's magnetic field is, this is Earth's magnetic field for context, so much, much smaller than Jupiter's. There's lots of weather patterns that we see in the clouds in the upper atmosphere of Jupiter. So this is an infrared image, and you can basically see like a Congo line of what would look like hurricanes on Earth, kind of moving around the polar region of Jupiter. And of course, the most famous weather on Jupiter is the Great Red Spot. So this is another huge storm in the atmosphere of Jupiter. So just this one storm is twice as wide as the Earth. And people have been looking at Jupiter with telescopes for a long time, and we've seen this storm for at least 3 centuries. So a storm twice as big as the Earth that has lasted for at least 300 years and probably longer. There's lots of different colors when we look at the clouds on Jupiter. There's bands of white, there's oranges, there's browns, and those different colors will correspond to different chemical signatures. So Jupiter is mainly hydrogen, but that hydrogen can make compounds with other elements to make different molecules. So the upper level of the atmosphere, so these are the white clouds. This is when hydrogen can make ammonia. Then a little bit deeper, and therefore a little bit colder, you could get ammonium hydrosulfide forming. And then colder still, you can get water clouds. So that's hydrogen and oxygen together. And so the different layers that you're seeing, they might not all be at the same altitude. Instead, you can have different depths into the atmosphere when you're looking at the different colors. So the ammonium sulfide are the kind of red-brown clouds, and then just the pure ammonia are the white clouds. So we said that Jupiter's core is not like a big ball of iron like the Earth's is. So how does Jupiter make a magnetic field? So to make a magnetic field, you need charged particles that are basically moving around in a circle inside of your planet. So Jupiter has that layer of metallic hydrogen, and so the planet is spinning, and so you get charged particles moving in a circle that'll generate a magnetic field. And so that's how Jupiter has a magnetic field. So it's same idea as the Earth in that charged particles are moving, but on the Earth it's due to the charged particles moving around an iron core, and in Jupiter it's the metallic hydrogen that is circulating. So another way that we can study the atmosphere of Jupiter is by watching what happens when something hits Jupiter.
The lasting impacts of comet Shoemaker-Levy 9. Presented by Science at NASA. At the close of the last century, a comet captured into orbit around a planet traveled too close and was shredded by its gravity into multiple pieces, some as large as half a mile or 1 kilometer long. Those fragments would plunge into the planet's atmosphere in a series of impacts. Would the impacts be spectacular, or would the comet fragments disappear without a trace? In July 1994, astronomers around the world watched with bated breath as the fragments of comet Shoemaker-Levy 9 slammed into the planet Jupiter. Dr. Kelly Fast was one of the impact's observers and is now manager of NASA's Near-Earth Object Observations program.
It was just incredible to watch. Such an impact event had never before been witnessed, let alone studied. Ground-based telescopes around the world and spacecraft like NASA's Hubble Space Telescope and even the Galileo orbiter en route to Jupiter were used to observe the impacts. The discovery of the comet by Carolyn and Gene Shoemaker and David Levy gave us about a year to plan our observations.
The impacts proved to be impressive. The fragments, some 21 in all, plunged into Jupiter's atmosphere over the course of 6 days. At impact, they were traveling at a speed of about 37 miles per second, or 60 kilometers per second, heating the atmosphere to at least 53,000 degrees Fahrenheit, or 30,000 degrees Celsius. Like the splash from throwing a rock into a pond, the impacts created giant plumes of material from Jupiter's lower atmosphere, which rose as high as 1,900 miles, or 3,000 kilometers above the cloud tops into the stratosphere. In the aftermath, the plume splashback scarred Jupiter's atmosphere with dark clouds of impact debris, which could be seen for months as they were gradually dispersed by Jupiter's winds. So what were scientists able to learn about Jupiter itself as a result of the impacts? For one thing, those dark clouds of impact debris acted as tracers of the winds in Jupiter's stratosphere, and by following their motion over time, scientists could measure those high-altitude winds. Temporary changes in the aurora on Jupiter showed scientists that Jupiter's magnetosphere was influenced by particles from the impacts.
We are still able to see changes in Jupiter's atmosphere that resulted from the impacts. When the fragments of Shoemaker-Levy 9 slammed into Jupiter, they deposited their own chemical compounds, the impact processes produced some, and others were exhumed from the lower atmosphere. Some molecules, like ammonia, were destroyed by sunlight in the weeks and months after the impacts. But others, like hydrogen cyanide and water, are still seen today. All of that tells scientists about how chemistry works in Jupiter's atmosphere.
Comet Shoemaker-Levy 9 showed us that large impacts still happen in the solar system and were a factor in NASA developing programs to address the impact risk to Earth. From comet science to Jupiter science to the science of impacts, the legacy of that serendipitous discovery by Carolyn and Jean Shoemaker and David Levy continues to this day and into the future. For more impactful stories about comets and asteroids, visit science.nasa.gov.
We were able to use the impact of a comet into Jupiter to study its atmosphere and the weather patterns, which I think is pretty cool. So, unlike the terrestrial planets, which either have no moons or one moon or a couple of captured asteroids as moons, the gas planets have many, many moons. So Jupiter has, at the time I made this slide, 95 moons, but people are finding new moons, not every day, but there's a possibility that there are still more to discover. And so the 4 moons pictured here are the Galilean moons, and these are the moons that Galileo was able to observe with his telescope from the Earth. And so those 4 moons going from closest to Jupiter outwards are Io, Europa, Ganymede, and Callisto. Io is very interesting because it's the most volcanically active object in the solar system. And so these are all pictures of Io. I think the one on the right in the infrared is probably the most telling. All of those red spots are active volcanoes on the surface. There's also large plumes coming off from the surface, and we talked about how some of that material ends up hitting the magnetic field lines of Jupiter and ending up in the creating the auroras on Jupiter. So why is this moon one of the most, or the most, volcanically active body in the solar system? So it has to do with tidal forces that we learned about earlier. So as the moon is orbiting Jupiter, there will be a tidal force. So basically the side that's closest to Jupiter will feel more force than the side farthest from Jupiter, and you stretch the planet a little bit. And so the side that's closest to Jupiter is going to change as it orbits, and so you'll get these stretches and squishes in different directions. And so that basically stretching and squishing the planet constantly causes heating within the interior of the planet. And so the tidal forces are so extreme that the inside of the planet or the inside of the moon is very hot, and so you get a very geologically active planet with lots of volcanic eruptions. The next Galilean moon out from Jupiter is Europa, and this is what its surface looks like. So there's lots of cracks, there's different colors on the surface. So what are we looking at? So unlike the terrestrial planets, which are made out of rock, these moons are made out of ice. So this surface is ice, and so the cracks that you're seeing are basically cracks in that surface layer of ice. However, we think that it's not a complete ice ball all the way through, and we think that there are liquid oceans underneath the top layer of ice. So how is the interior of Europa still warm enough for the material to be liquid instead of a solid? The same reason that Io is so volcanically active. So Europa is under the influences of tidal forces. Those tidal forces are going to generate heat within the planet, and so there's a layer of liquid underneath the top crust of ice. And so the cracks that we're seeing are basically the layer of ice moving with respect to each other, kind of like we have our plate tectonics on the Earth. You get different chunks of ice moving on top of the liquid underneath. So this is a cross-section of what we think the interior of Europa looks like. It has a metallic core, maybe some kind of rocky material, and then we think this layer of liquid water, and then an outer crust of ice. And so you can have convection cycles in this layer of water, bringing hot material up, melting some of the surface ice, and getting patterns like this that you see on the surface. And so when we start talking about where we might find life outside of Earth, this is one place that has scientists very exciting, because one of the things we said we needed was liquid water. So this is not liquid water on the surface, but it is liquid water, and so if we could ever study what's down here, maybe we could find life. Life on Earth, we find, obviously our oceans are full of life, and even around hydrothermal vents on the ocean floor, those are very good places to find life. So maybe underneath this icy layer on Europa, we can find life in this liquid water ocean. The next moon out from Jupiter is Ganymede. This is actually the largest moon in the solar system. There's clear evidence of geologic activity. You can see these streaks of different colors. You can see areas where the surface is much smoother, and so it's newer, has less impact cratering. And again, where is this moon getting the energy to have geologic activity? We think it's some kind of combination of tidal heating from orbiting Jupiter, and just like we have in the Earth, some radioactive decay and towards the center of the planet, giving it some residual heat. And then the last moon out is Callisto. This is your typical ice ball, basically. So this is a thick ball of ice that maybe has some rocky material and some metal towards the center. It's too far away from Jupiter to have tidal heating, and the orbital resonance is about how interactions with the other moons might also give it some tidal heating, but it doesn't have those either. but it does have a magnetic field. And we've said that you can't have a magnetic field if you're geologically dead. So there must be something happening under the surface of Callisto to give it a magnetic field. So the current hypothesis is some kind of liquid water under the surface like we had on Europa that is inside of the water. There's going to be some kind of ions, like if you dissolve salt in water, you can have ions floating around. So you have charged particles moving around in a circle. Charged particles moving around in a circle gives you magnetic fields. So the moons of Jupiter are just as interesting, if not maybe more interesting, than some of the planets that we've talked about so far. So how does Io get heated up by Jupiter? So tidal forces. So anytime we're talking about Jupiter's moons getting any heat that they're receiving is from tidal forces. Jupiter's not big enough to do nuclear reactions. The magnetic fields don't really generate heat, and Jupiter itself doesn't have any volcanoes, but its tidal forces cause volcanoes on the surface of Io. The next planet out from the sun is Saturn. This is a lot of people's favorite planet just because of the magnificence of its rings. And it looks kind of similar to Jupiter. It has similar colors, but a little bit less activity. It's farther from the sun, so it receives less energy from the sun, and so less energy to power the atmosphere, basically. But that's not to say there aren't weather patterns in Saturn's atmosphere. So this is a picture taken from Cassini, which is a probe orbiting Saturn, and so you can see this cloud pattern from a storm on the surface of Saturn. And this is a series of images taken for this really weird hexagonal storm at one of the poles of Saturn. So the reason it's a hexagon has to do with some physics about how things move on a sphere, but just a really interesting, like imagine if you had a hurricane on the Earth that was a hexagon shape. Just like Jupiter, Saturn has a lot of moons, so Saturn has even more than Jupiter, 146 that we've seen, and again, there might be more discovered in the future. You have very large moons like Titan and Enceladus, and then you have these smaller moons that are balls of ice that show some evidence of past volcanism or tectonic activity, but that we think are currently dead. And you have interesting ones like Mimas that kind of looks like the Death Star. So what geologic activity do we see on Titan and other moons? So this is an image of Titan, and what you might notice is it's got some thickness around it, and that is an atmosphere. So Titan is the only moon in the solar system that has an atmosphere, and the atmosphere is mostly nitrogen with some other chemicals. On the Earth, we said that having an atmosphere was one of the things you needed to support life. And so this is another place that scientists are excited about as maybe a place we can look for life. So we've sent probes to Titan, and we've landed something on the surface. So Huygens was a probe that came from the Cassini spacecraft that I mentioned that was orbiting Saturn. And so this is a view of Titan, and then as the Huygens probe is landing, you can see some of the landscape and then what the surface of Titan looks like. And so this is a ball of ice. So the rocky material that you're seeing, these are not rocks made out of silica like we have on Earth. These are rocks that are made out of ice. So the surface of Titan is water ice. We think that there might be liquid on the surface of Titan, but again, it's too cold for that liquid to be water, so we think that liquid is methane. So if you are a biochemist, an area of research that you could go into is how do I make life work with where liquid methane is the liquid instead of H2O as the liquid to support life. And is that even possible? So this is what Titan looked like as the Huygens probe was landing. And so those rocks that we saw on the surface were pretty rounded. And so that's evidence that there's some kind of erosion, whether that's from the atmosphere or from water flowing across the surface, is to be determined. So this is radar imaging, so this is radio wavelength, and so you can see what appears to be large lakes or seas on the surface of Titan. But again, it's too cold for that to be liquid water, and And so instead this is liquid methane. And as the video said, those lakes are confined to the polar regions, and where the probe landed was not in the polar regions, and so it didn't encounter any liquid. Okay, another interesting moon of Saturn is Enceladus. So if we look at this bottom cutout, there's material that's being erupted from within the moon, and so there's evidence of geologic activity going on inside of Enceladus. And so kind of an interesting thing to think about, on the Earth, when we have a volcano erupt, it's spewing out magma, which is molten rock. But Enceladus is made out of ice, so the volcanoes on an icy surface are going to be putting out water, because the interior of the ball is made out of ice instead of being made out of rock. So the volcanoes, or ice volcanoes on Enceladus, are putting out water and water vapor into space instead of putting out molten rock. Okay. So we talked about Saturn and we haven't talked about the rings. So we're going to talk about the rings of Saturn, and as it turns out, all of the other gas planets have rings of their own. So what are Saturn's rings like? These are not solid material that's orbiting the planet. Instead, these are very small particles of ice that are orbiting the planet. And so they orbit around Saturn's equator, and they are very thin. So it's not a thick layer, and it's not a solid object. It's many tiny objects all orbiting together. So this is what Saturn looks like through a telescope on the Earth. There's this dark void in the middle of the rings called the Cassini division. This is a very famous picture on the left. So this is a probe that was sent towards Saturn, and so they're taking a picture of Saturn and its rings. And then, can anyone guess what this arrow is pointing at? Yep. Yeah, so this is the Earth. So this image is called the pale blue dot, and so this is what the Earth looks like from Saturn. And so it's not just that big dark gap that we saw in Saturn's rings, but there's lots of small gaps all throughout the rings. And so those gaps are a result of tiny moons orbiting Saturn. So really you can think of the rings themselves as all being satellites orbiting Saturn. And when one of those chunks of material is rather large, then it will clear everything else out of the part of its orbit, that part of the circle that it orbits around. And so any of the gaps that you see are due to these gap moons, or shepherd moons, as you might also hear them called. So like I said, all of the gas planets actually have ring systems. They're just not all visible in visible wavelength light. So if you look at Jupiter through infrared light, you can see its ring system. Saturn, obviously, we can see that with visible wavelength. Uranus, you can see its ring system in the infrared, and Neptune is very far from the sun, so from the Earth you're probably not going to see its ring system, but we have sent probes out there, and in the visible wavelength light you can see its rings. So Saturn, the material that makes up Saturn's ring is just very reflective in visible wavelength light, but the rings of other gas planets are different material, so they're either smaller or darker, and so they don't reflect the sunlight as well. So why do all of these gas planets have ring systems? So you need a lot of small material orbiting your planet in order to make a ring, but these are not leftover material from when the planet formed. You might have a ring system that lasts for a very short time after your planet forms, but it will very quickly dissipate. So you need some kind of continuous input of material to maintain your ring system. And so this is where having all of those moons comes into play. So the moons that are orbiting these planets are not necessarily all in very nice and distinct orbital paths. So you can get different moons to hit each other, and all of the debris that comes out when two moonlets, or moons that are in the process of forming, anytime they hit, you can have a lot of material recycled back into the ring system of your planet. And these gas giants are very big, they have a lot of gravity, and so there's tidal forces that keep any moons that are too close to the planet from being able to form a nice spherical moon shape, and so there's lots of material available for collisions to populate your ring system. And the rings of Saturn are not necessarily going to last forever, so we're fortunate that we live in a time where we can see them, and especially in the visible wavelength. So the rings of the gas planets are made out of very small particles, and there's lots of gaps within those particles due to the gap moons. And in order to have a ring system, you need a lot of material to make those rings, and that material comes from moons and moonlets colliding and giving you a bunch of material.